Welcome to This Explainer. Today, we're diving into something that sounds a bit intimidating, but is actually super cool. We are going to completely demystify a complex laboratory term and show you exactly how scientists decode the invisible mixtures that exist all around us. We're going to break down the science and the art of chemical separation so you can literally see the unseen.
Picture this: a smeared ransom note at a crime scene, a doped athlete trying to cheat the system, or maybe contaminated drinking water. What do all these high-stakes scenarios have in common? Like, how do investigators actually figure out the invisible chemicals hiding in plain sight when everything is mixed together?
Well, the secret weapon is a process called chromatography. I know, it's a big word, but at its core, it's just a lab technique used to separate, identify, and quantify the different parts of a mixture. You can think of it like taking a giant, messy, mixed fruit basket and magically sorting it into perfectly organized piles of apples, oranges, and bananas. What looks like one chaotic jumble is actually made of distinct, totally separable parts.
So here is our roadmap for today's explainer. First, we'll decode everyday chemical mysteries. Next, we're off to the great chemical race, followed by sticking, dissolving, and measuring. Then we'll open up the chromatography toolkit and finally wrap up with some real-world scientific superpowers.
All right, let's kick things off with Section 1, the Great Chemical Race, where we'll unpack the core principles.
To really get this, imagine four friends walking down a super muddy road. Ali is sprinting. He just wants to get to the end. Ahmad is walking pretty slowly. Bilal, he keeps getting his shoes completely stuck in the thick mud. And Hassan, well, he keeps stopping to take pictures. Because they all interact with that muddy road differently, some running, some getting stuck, they naturally spread out and separate over time. And guess what? This is exactly how chemicals behave. Different substances move at entirely different speeds based on what they're attracted to.
So, if we take that muddy road analogy and apply it to actual chemistry, we get two really vital components. First, there's the stationary phase. This is the fixed track, right? Like paper or silica gel. Then we have the mobile phase. This is basically the wind or a bus carrying the passengers forward, usually a liquid solvent or a gas.
It's honestly helpful to give these chemical components personalities. They are constantly fighting a tug-of-war between two urges. One part is saying, I want to stay. That's the attraction to the stationary phase. The other part is screaming, I want to move, getting pulled by the mobile phase. Whichever urge is stronger determines exactly how fast and how far that specific chemical is going to travel.
Moving right along to Section 2, sticking, dissolving, and measuring. Let's look at the actual mechanics of separation.
Okay, so there are two main physical mechanisms driving this whole process. First up is adsorption. This is when components physically stick to a solid surface, kind of like dust clinging to your living room furniture. The second is partition. This happens when components distribute themselves by dissolving between two liquids. Think about how sugar completely dissolves in your hot tea, whereas oil wants a totally different liquid. These physical interactions are the hidden engines driving the whole separation.
Let's visualize this. Imagine taking a single drop of black ink, putting it on a piece of chromatography paper, and just dipping the bottom edge into water. As the water, our mobile phase, remember, creeps up the paper, it carries the dyes with it. But here's the catch. Some dyes prefer the paper, while others absolutely love the water. So right before your eyes, that single black dot miraculously separates out into distinct blue, yellow, and red dyes.
In the final result of all this, it's called a chromatogram. This is essentially the visual finish line for our chemical race. Depending on the technique you're using, it might look like a piece of paper dotted with distinct, colorful spots. Or, if we're talking high-tech lab equipment, it's a computer graph showing a series of sharp peaks. Either way, it tells scientists exactly where our little chemical runners ended up.
But how do we actually measure the winners of this chemical race? Well, in advanced methods like gas or liquid chromatography, scientists calculate something called retention time. This is literally just tracking how many minutes a specific compound stayed inside the stationary phase before finally crossing the finish line at the detector. So, compound A might sprint across at 3 minutes, while a stickier compound B takes, say, 5 minutes.
Now, for simpler setups like paper chromatography, we use a metric called the retention factor, or RF. And the math here is beautifully simple. You just take the distance your compound moved and divide it by the distance the solvent moved. That's it. So if your chemical moves 4 centimeters and the water solvent moves 8 centimeters, 4 divided by 8 gives you a clean RF of 0.5. It's a highly precise way to put a number on that separation.
Next up is Section 3, the Chromatography Toolkit. Let's explore some specialized types and techniques.
When we crack open the modern chromatography toolkit, we find some incredibly specialized gear. Gas chromatography, for instance, uses inert gases to separate volatile stuff like perfumes. Then there's high-performance liquid chromatography, or HPLC. This literally forces liquids through tightly packed columns under extreme pressure, which is absolutely perfect for testing pharmaceuticals. And size exclusion chromatography? It traps tiny molecules inside porous beads, letting the big ones rush right past. It literally sorts them by size.
But wait, it gets even more specific. We also have methods like ion exchange chromatography, which uses electrical charges to bind oppositely charged molecules, super handy for purifying amino acids. And then there's affinity chromatography. This one uses a highly specific biological lock and key mechanism to grab only the exact molecules you want, washing everything else right down the drain.
All right, let's bring it all home with Section 4, Real-World Scientific Superpowers, covering applications, pros, and cons.
The advantages of these techniques honestly give scientists borderline superhuman abilities. Chromatography is insanely accurate, fast, and incredibly sensitive. The craziest part? It requires only a tiny microscopic drop or a single fiber of a sample to completely unravel the most complex chemical mixtures imaginable into pure, identifiable parts.
Of course, it's not perfect. There are limits. Those extreme pressure machines we talked about, they can be incredibly expensive. You also need highly skilled, specially trained operators just to run them and read the graphs. On top of that, you sometimes have to handle costly and frankly hazardous chemical solvents to create your mobile phase. But despite those hurdles, chromatography is actively working behind the scenes pretty much everywhere in your life. It's wild how widespread it is. It's used by forensics teams to analyze blood at crime scenes. It's used by the pharmaceutical industry to guarantee the medicine you get at the hospital is perfectly pure. It's even testing your drinking water for pollutants and keeping sports fair by sniffing out microscopic trace amounts of banned drugs in athletes.
Ultimately, chromatography proves that our physical world is incredibly dense and complex. What looks like a single, simple substance, whether that's a drop of black ink, a glass of water, or a medical pill, is actually a bustling, complex crowd of chemicals all running their own race. And that really leaves us wondering, what unseen chemical mixtures are hiding in plain sight around you right now, just waiting to be separated?